Okay, everyone, we're gonna get started. Okay. Welcome everyone to the first Biomes talk of the semester. My name is Dylan Judd. I'm a second year doctoral student at YSE and a new member of the Biomes committee. We are very excited to host such an esteemed lineup of speakers this semester, and we hope you're all excited as well. Over the last 12 years, BIOMES, which stands for Bridging Issues and Optimizing Methods in Environmental Studies, has been the school's flagship forum for bringing cutting-edge research and impactful work to the YSE community. Today, I have the privilege of introducing one of our own and one of my advisors, Dr. Paul Anastas. Paul Anastas is a professor of environmental health sciences at the Yale School of Public Health and holds the Teresa and H. John Heinz Chair in Chemistry for the Environment at the Yale School of the Environment. In addition to these roles, he holds appointments at the Department of Chemistry, the School of Engineering and Applied Sciences, and the School of Management. Trained as a synthetic organic chemist, Anastas is the inaugural director of the Center for Green Chemistry and Green Engineering here at Yale. His extensive experience outside of Yale includes serving in 4 presidential administrations, which involves leading the Environment Division of the White House Office of Science and Technology and being appointed by President Obama to serve as an assistant administrator for research and development at the EPA. An accomplished scholar, Anastas has co-founded 5 companies, authored over 200 peer-reviewed papers with more than 42,000 citations, and published 17 books on sustainable technologies. He has also been awarded 9 honorary doctorates from institutions across Asia, Europe, and the Americas. Among his numerous honors are the Volvo Prize, the Heinz Award, the E.O. Wilson Award, the Rachel Carson Prize, and the Von Hoffman Medal. However, he recently shared with me that his proudest accolade is the teaching award that he won from YSE in 2024. So, without further ado, please join me in welcoming Paul to the stage.
Wow, listening to that introduction, I feel tired. And to accomplish all of that at the age of 35, who would have thought of that? It is a gift to be able to be invited to speak to a group that I have tremendous respect for about a topic that I think is tremendously important. And I'm going to take you on a journey with the time that we have here and talk a little bit about the different work that's being done in my labs right up the hill in Greeley. But I don't ever want to suggest that I have done this alone. Right now in this room are members of the Center for Green Chemistry, Green Engineering, my research group. If y'all wouldn't mind standing up, please. Please. Thank you. I am so lucky to be associated with you, and I get to tell our story. Now, at Yale, we're told that we're supposed to be recognized for doing curiosity-driven research and hypothesis-driven research. Well, when I showed up here, one of the things that I have to say that I was particularly curious about is whether we could design and reinvent the material basis of our society and our economy so that it's actually sustainable. And the hypothesis that I brought to it is, yep, we could. What this journey this afternoon is going to be about is showing just some illustrative examples of some of the discoveries, some of the inventions, but perhaps at least as importantly, the context behind all of this and the impact of these inventions. So I call this, where would you like me to point? Oh, God bless you. All right, call this Designing Tomorrow. How do we think about how we design and invent things material basis, including the materials used to generate, store, and transport our energy, so that it's different from today, so that it is healthful rather than toxic, renewable rather than um, finite, and restorative rather than degrading. So it won't shock you that since I'm a chemist, I think that the basis of everything that we see, touch, and feel is a chemical. I'm pretty certain that you can't name anything in this room that isn't breathing, that isn't a chemical, and everything that is breathing is a chemical. So because of that, we reflect on the fact that 150 years ago, chemistry started changing the world. So many of the issues that we all talk about, that we dedicate our focus toward, are being driven by the nature of the chemistry that we use, whether it is for, as we said, energy, whether it's in the way that we grow food, whether it's the materials that we use in our daily lives, the things that we slather all over our body in the shower, that on and on and on, the clothes, you name it. So 150 years ago, chemistry started changing the world. And since I'm guessing a good portion of us want to change the world, I'm going to suggest that you can't change the world if you don't change the chemistry. Now, I'm going to hope that you give me the benefit of the doubt that I don't think chemistry is important because that's what I do and that's what I've done. Hopefully, you give me the benefit of the doubt to say that I did it because I thought it was important. So we take a look at this periodic table back when Mendeleev first introduced it back in 1869, and we know that it wasn't complete then. There was a lot that we didn't know. There was a lot that didn't need to be filled in. And over the years, we wound up having this more complete picture so that we could actually predict how things behave and interact. One of the greatest Rosetta Stones ever assembled. The power that this periodic table gave us is immense, and still we are only scratching the surface of its brilliance. But we start thinking about, all right, I've been thinking about how do we tell this story of what we do up the hill. And I realized that as we pursue sustainability, it certainly has to start with the humanitarian drivers. And that's why we do green chemistry and green engineering, in order to meet those humanitarian needs. But we're going to need enabling system conditions in order to transform those discoveries and those inventions and those innovations into reality, into impact into people's lives. And of course, we're always going to be striving toward those noble goals, those over the horizon views of perfection that we want to achieve, right? There are so many aspects to these ambitions that we're striving towards, so many elements, if you will. Took me a long time to make this slide, so this is the periodic table of green and sustainable chemistry. All of these elements are aspects of why we do what we do, how we do it, and how we enable it in order to bring it to scale in the time frame that's necessary and relevant. I'm going to spend our time together to walk us through this just a little bit. So the why we do it. It won't shock you because of the color coding that this is directly related to the 17 Sustainable Development Goals. And there might be some folks who would say, oh, chemistry might be related to 3, 4, who knows, maybe even as many as 10. It won't shock you to know that I believe that it's absolutely essential to all 17. And hopefully we'll try to demonstrate this, because what we're talking about is when we are discussing chemistry, we're not talking about an academic department or an industrial sector. We're talking about everything that we see, touch, and feel. So if you're talking about clean water, clean land, growing food, empowering the economy, since 96% of all of the manufacturing economy is touched by chemistry. And I can't think of the other 4%. When we talk about the molecular basis of sustainability, just a slight illustration is, do we think that the nature of our current energy is directly impacted by the strength of the carbon-hydrogen bond, or the carbon-carbon single bond? Do we think that stratospheric ozone or persistent is related to the strength of the carbon-fluorine bond, or the toxicity and carcinogenicity is related to the carbon-carbon double bond, or the stretching bonds of CO2 is related to global warming, or the nitrogen-hydrogen bond being related to our food supply? The answer is, of course, yes. But it's also not only yes, it's non-trivial. Because of the nature and the character of our materials impacting all of these issues, it cascades through our society and our economy, and this is the important part, it's amenable to design. Because we are able to impact what the materials that we use are, we're able to impact some of the great grand challenges of our generation. So we come back to this periodic table and why we do it. We're going to move on to how we do it. What is it that you're doing up there in the basement of Greeley all the time? So we're going to give, what we're doing is green chemistry. For those of you less familiar with green chemistry, it's all about how you design chemical products and processes so that you reduce or eliminate the use and generation of hazardous substances. Hazards of all types, not just toxicological hazards, physical hazards, global hazards, resource depletion. Yes, of course, climate change, and on and on. Now, is this just a wonderful academic theory that sounds nice? Well, a number of years ago, we put out a paper called The Green Chemist Tree, using the tree metaphor for the fact that each of these leaves is a new platform, a new technological platform that has been invented, introduced through green chemistry. These platforms are being integrated across industry sectors, sending the message that so many of our approaches to protect the environment, to protect human health, have been too often about what you can't do, what you have to stop doing, what you have to minimize, what you have to ban, what you have to phase out. Green chemistry is about what you can create, what you can invent, what you can innovate. And these are just some of the, a zoom in of the technology platforms, but what's most important is it touches all aspects of our society. So if we say, oh, is green chemistry an energy technology? Yep. Agricultural technology? Yep. Can go on and on. So a few years ago, science asked a few of us to write a piece on chemistry for tomorrow's Earth and the future of chemistry. And really, this framework is talking about where we've been for the past 150 plus years and where we're going. What's astounding is if you read through this, and it would take me a semester to explain it, you'd say, oh, well, of course this makes sense. It's almost trivial. It's so obvious, Paul. It bears almost no resemblance because the vast majority of what we do still today, is in the old way of 150 years ago. Now, the great news is that there are countless green chemistry achievements that we've been talking about, but it's still the exception and not yet the rule. So this framework about how we go about a decision tree to make sure that something certainly functions, but it's going to be renewable rather than toxic, that we're going to use all of the lessons of the integrated biorefinery, I should say of the petroleum refinery, and put it into the integrated biorefinery. What I will say is that the oil industry didn't conquer the world by saying, oh, we've got some black goo coming out of the ground. Maybe we'll make some gasoline and forget about the rest. It did it by squeezing value out of absolutely every distillation fraction that it could. But yet, when we look at the history of biofuels, it has been, let's make some biodiesel and cut on government subsidies. What we're doing up there in Greeley and around campus is, how do you squeeze value out of absolutely every distillation fraction, and more importantly, transforming those different fractions into value. So yes, making sure it's renewable, but also making sure that it's inherently non-toxic as it possibly can be by design. Safe and sustainable by design is finally something that is being realized and being built into frameworks in Europe. And ultimately, you want to say that your final product, performing well, renewable, non-toxic, at the end of life, it's either going to be able to be put into a circular system, or if it's got a dissipative use, is going to be able to degrade harmlessly into the environment. So this is the framework. So how do we wind up turning these frameworks that we've put out there into reality? Some of the inventions that are being carried out up there include this, this one example of bio-based surfactants. Now, I'm telling you, I could talk to you a lot about C glycosides and watch you doze off, so I'm not going to do that. But what I am going to do is tell you that these C glycosides, these bio-based surfactants, are crucial for one big reason. Because these surfactants are in just about every formulated product you use. When I say a formulated product, I mean typical mixture, whether it's a cleaner, whether it's the cosmetics, personal care, anything that as you walk down the aisles of your grocery store or CVS has these surfactants in it. They've always been petroleum-based and at best of questionable toxicity. So making these renewable is not a small thing. Really easy to make it an O-glycoside through the oxygen, but making it through the carbon was something that was a challenge for decades. We were lucky enough to solve this problem and patent this this particular class of chemicals, and wound up. We'll get to the rest of that story in just a little bit. When we start looking at lignin, here we are in our history of forestry school and forest, and we're going to talk about wood. We all know that lignin is the basis of all woody plants, structural, and everybody knows that lignocellulose is very valuable, but everybody uses the cellulose. Lignin, still today in 2025, is 98% burned. Yet, it is the only natural source of any consequence to produce aromatic chemicals being so valuable in our economy, those ring chemicals. But you need to be able to break it down. Being able to develop a mild way of breaking down lignin has been something of a holy grail. We were lucky enough to develop this with a simple, called a copper PMO catalyst, in order to make these molecular building blocks. Again, we're going to return to the rest of this story in a little bit. And yes, we were able to patent this particular technology. There's a whole lot of natural products that are out there in nature that are plentiful in agricultural waste. They're plentiful in timber wastes. But yet, we never knew how to utilize them. Why? Because we spent the last 150 years figuring out how to modify hydrocarbons. And so the biggest, most important thing that you can do in chemistry is come up with a new pair of molecular scissors to break down molecules, or some molecular glue to put things together and build them up. That's pretty much what we do. This is a pair of molecular scissors able to transform these plentiful and, quite frankly, very cheap starting materials into valuable classes of chemicals called aldehydes that are useful as a building block throughout the chemical sector. I will mention that this is a sodium magnesium catalyst. And one of the things that we were able to do is using phytoremediation, that is plants sucking up pollutants out of the ground. You always say, oh, that's great. The plants can suck up all the pollutants out of the soil and clean the soil. What happens to the plants when they're all, you get a whole bunch of contaminated plants? But if you're able to take those plants, calcine them at high temperatures, and use them as extraordinarily potent catalysts, then that is a great solution. Going to how you produce green hydrogen. We've known how to split water for forever. We haven't known how to do it very well or very efficiently. Being able to develop instead of using something like iridium, we instead pivot to this particular catalyst, which is 10,000 times more plentiful, 10,000 times less costly, and able to split not only water, but seawater. Splitting seawater selectively, cheaply, quickly, and efficiently, and producing green hydrogen, well, that all sounds nice, but who cares? Why you care is because one of the reasons you care is because if you want to generate renewable power and you want to store it, since right now we all know that so much of our renewable energy is generated and lost, hydrogen provides an amazing storage container for renewable power, where you can store it as hydrogen through the splitting and then reclaim it with a hydrogen fuel cell or other mechanism. But you have to, after generating, you do have to store it. And storage is not trivial. Yeah, we were able to patent that discovery as well, the splitting of hydrogen. And we'll come back to that. Looking at how you store it. You want to store it in hydrogen in an inert material that not only stores a lot of this stuff, but it's super easy to remove it again, to get it to come out. That's wicked hard, as we say up in Boston. Wicked hard. But we were able to develop this thing called an ammonia borane that is able to store tremendous amounts of hydrogen, and yet, under extremely mild conditions, release it and allow it to be able to be used for, as we said, fuel cells or other purposes. Other purposes, Paul? What do you mean by those other purposes? You're being mysterious and cryptic. No, I'm not. When you have your green hydrogen, what do you want to do with it? You want to do something that when I was sitting in your metaphorical chairs, I was taught that you must not go on the foolish endeavor of thinking that you're going to convert CO2 into something valuable. Harumph-rump, it is in too low of an energy state, harumph-rump. Unless you're a plant, put that out of your mind, young chemist. The ability to convert CO2 into valuable products, captured CO2 into valuable products. I hope that someday the collection of people doing this kind of work, as well as ourselves, will be viewed as one of the great breakthroughs of turning some of our biggest problems into some of our biggest opportunities. Using that green CO2, green hydrogen with captured CO2, right now up in our labs, we're working on conversion this to various alcohols, methanol, ethanol. Yes, various chain hydrocarbons. Hydrocarbons, you mean the kind of things that we put in our car and drive around? Yes, except these are not fossil. These are the same hydrocarbons that are drop-in molecularly identical to what you use every day, but yet they're from captured CO2. Various sugars and polymers are all now accessible. And why is that important? We put out this framework, if you're interested in this paper. This is called the CO2 tree. We like tree metaphors. this is looking across the various oxidation states of carbon, all of the different building blocks that can be made that are currently accessible. This review has over 300 reviews of uh, different demonstrated conversions of captured CO2 into these building blocks. If you are interested in that paper, you can scan the QR code. Hannah, when did this paper come out? A month ago? 2 weeks ago? 2 weeks ago. So you always worry about review papers going out of date. This one's still right there. So converting CO2 into useful products is tremendously important. Coming back to wood, I gotta confess, when I showed up here, I had this idea that maybe we would be able to make synthetic wood. Why did I want that? Because nature is brilliant and there's pretty much, to a first approximation, nothing as good as wood. Wood is awesome. Wood is, it's so astounding. And people were focused, including ourselves, on breaking down wood into the building blocks, and we did that. And what I wanted to do is not just break it down, but put it back together and make new wood, tailored wood, designed wood, taking advantage of all of nature's brilliance with new morphologies, with new performance, and we've just scratched the surface with some of this latest work. Yes, breaking down the wood, making the building blocks into our own molecular Legos and putting them together in ways that just have our minds dancing about the potential of what new synthetic wood could look like, could do, the performance that it can impart. Instead of burning 98% of that timber waste, that lignin, how do we take advantage of its brilliance? Then we have issues like polyethylene. Polyethylene, you know, we're all correctly wringing our hands about the um, plastics waste, microplastics, oceans plastics, pardon the cough, um, oceans plastics, and we know that it persists for millennia. Why? Because of the nature of the carbon-carbon bond. And the idea of taking polyethylene, which is produced in well over 100 megatons every year. How do you take this and deal with it? Well, to deal with it, you might want to first come up with a way of breaking it down using a particular catalyst that we invented. And then, do you just want to break it down? Really, you just want to break it down into ethylene? Yeah, you could do that. Or you could combine it with CO2 and turn it into a new class of polymers that have performance characteristics similar or better in many cases to that of polyethylene. So you're just turning one of our biggest material problems into a potential solution. So this is, that patent was just filed within the past few weeks, and that is the paper that was just accepted by Wiley. So just very quickly, I'm just going to say some of the most hazardous, nastiest, dirtiest, filthiest, horrible chemistry that exists out there is nitration chemistry. I won't get into it except when you're combining sulfuric acid with nitric acid and the fumes, and that there's a reason why that's almost never done in the US, because the US ships off these things to other places to take care of their dirty, filthy, hazardous chemistry. Did he say that out loud? Yes, I did. So what we wound up doing is going from this old way of doing nitration chemistry, and with, yes, a little bit of salt, a little bit of a spark, we did electrochemistry. So all of the nitric acid, the sulfuric acid, the dangers, the hazards are eliminated from that across that life cycle. One area that would take me, again, at least a semester to discuss is the work we're doing using quantum modeling in order to design molecules de novo so that they have intrinsically reduced hazard. We have Dr. Petrovich and Tobias Mullers in the back who are working hard on this work. It's all about how do you understand the molecular nature of the substances and how they cross membranes, how they bind with receptors, and instead design it so that they're intrinsically incapable of carrying out those toxic mechanisms. The discoveries that we've had here are going to be talked about in just a second. Coming back to the periodic table, so that's just a flavor of what we do up there on the hill and around campus. How do we enable it? One of the things that is, a truth that needs to be confronted is that it's great to invent stuff. That's awesome. It's fun. It's good to discover stuff. It's good to innovate stuff. But if it doesn't go to scale, if it doesn't wind up being realized, if it's just an academic theory, well, that's not really what the folks at the center signed up for. So how we go about enabling it is through a variety of strategies. One is through awareness raising. And this is one example of a few years ago, we had 3, or was it 4, members of our center all realizing that they were expecting. And immediately it was, oh, well, what should we do since we're expecting and we're going to be working in the lab? And we realized there was, to a first approximation, nothing out there in the literature about what to expect when you're expecting in the lab. So they chose to do this comprehensive review of all of the questions that you'd ask. If you were a laboratory scientist and you were expecting, you would say, hey, could I please know about what I should be thinking about? And this went across all the different types of, toxic hazards, physical hazards, exposure hazards. And we put this out. It's a very lengthy paper that's being converted into a book. But it's also things like environmental justice. I'm going to try to go back. We talk about, for instance, the iceberg, where above the waterline, there are some issues of environmental justice that are quite obvious, that everybody knows, everybody talks about: proximity to a hazardous waste site or a fence line community that's downwind from a smokestack, toxic soil or things like that. Those are the obvious things, right? But there's so much more below the waterline. And below the waterline are those, everything from worker safety issues to lack of investment in a community to generational wealth and being diminished, and of course, health disparities, and we could go on and on. So one would probably be expected to say, what the heck does chemistry have to do with all of these complex socioeconomic issues? Well, this particular paper was about saying, by taking specific issues, specific actions in chemistry, how do you get a cascading impact such that by changing the nature of the feedstocks that come in, by changing the manufacturing process, by changing the way that you generate a particular material or plastic, or the nature of how it degrades, et cetera, how does that wind up cascading in order to positively impact things like worker safety, things like health disparities, things like investment? And so this is another awareness raising concept piece that was put out there. Dr. Lars Ratjen led a large effort on environmental health. This is something that we all are familiar with. So if I asked any of you, have you ever heard of studies being done on how air quality impacts mental health? You'd say, yeah, I've heard about that. If I asked you, if it said, have you ever been exposed to a study on how indoor air impacts productivity or cognition? You'd say, yeah, I've heard about that. And if I asked you, and what's the name of that field? You'd pause and you'd say, This framework is meant to bring together those fundamental pillars of how we know that environmental circumstances, environmental insults, environmental conditions impact the wide spectrum of mental health issues. And try to put that framework so that we can link these different studies and actually find out where the gaps are, where the understudied areas are, and move forward. We also work a lot on policy. How do we impact not just science, technology, and industry, but yes, the policy. And I have to say that we had been starting to work on this many years ago, well over a dozen years ago, in the initial drafts. Professor Zimmerman testified in front of the House Science Committee, I believe. Was it House or Senate? The House Science Committee, in support of this bill that was signed into law on January 5th, 2021. Did he say the 5th? Yeah, the 5th. And what is wonderful about this law, including all of the ways that it cuts across every agency of the government in order to mobilize investment and actions in sustainable chemistry. But what was perhaps just as important is it overrode a veto from the president. Just saying. Okay, so how do we take some of that work that we talked about on molecular design using quantum modeling and turn it into practical impact? How do we turn that into an enabling condition? This paper on toward property-based regulations takes a really hard look at how we have historically gone about doing risk assessments, risk analysis, cost-benefit analysis, in order to regulate chemical by chemical over years and decades. And it's slow, and it's ineffective, and it's broken. This approach saying, you know what, we actually don't hate individual chemicals. We hate hazard. And hazard is a derivative of the combination of physical chemical properties. So how could we come up with that collection of physical chemical properties in order to rethink and rewrite our regulations that would be far more effective, and at the same time as being more effective at protecting human health and the environment, would be far more beneficial to, I'll say it this way, innovative industry that wants predictability and guidelines for how they're going to be able to innovate without getting dinged by unpredictable and unstructured regulatory processes. A few years ago, we put out this framework saying the Environmental Protection Agency is a miraculous institution that has done fabulous things over 5 decades, and everything that gave it all of its successes that it should be so proud of are not the same things that it has to do for the next 50 years. How do you completely rethink and restructure what that winds up looking like to build in some of these drivers to innovation and, yes, designing tomorrow? Science asked us to do a paper that I was lucky enough to do with Professor Zimmerman about towards substitution with no regrets. Because one of the things that is true all too often is that we wind up making these substitutions. Oh, this is a terrible thing, methylene chloride, chloroform, phase it out, get rid of it, and the thing that's substituted for it is at least as toxic or worse. So this is a framework for how you are able to move forward without all of the unintended consequences. And this book that I was lucky enough to do with Dr. Petrovich, called First Do No Harm. I'm going to guess that there's not a chemist in the world that really wants to cause all the problems that we've caused for the past 150 years. But I'm wondering if we realize, if it's common knowledge, that there's not a single school in the world that I'm aware of where it's required that you know the consequences of the tools of your trade to get a PhD in chemistry. You don't have to know the molecular basis of toxicity. Can you think, maybe we can, this is a thought experiment. It's hard for me to think of another profession where you're not aware or responsible for the consequences of what you invent, what you design, what you introduce into the universe. So this book is all about, here's a guidepost, here's a framework, here's a decision tree. You don't have to, make things that are going to be toxic in this world. So as we think about why we do it, how we do it, and how we enable it, there's a few quick stories that I'll just finish up with. Because when I was telling you about those discoveries, those inventions, and I mentioned rather cheekily that, oh, we patented this one and we got the patent on that. It's all well and good to have a patent. But when you spin out companies that manufacture products, that employ folks, and change the nature of the things that we use every day. One of the first companies that we were lucky enough to spin out is P2 Science. P2 Science prides itself on being next generation chemical company. That all, if you remember that chart where we say the way that we used to do things and the way that we need to do things in the future, they're doing the way we need to do it in the future. The nature of the materials, the nature of the way that we transform them is part of the DNA of P2 Science. The good news is that it's being recognized for its innovation. It is being hailed as a next generation chemical company. And yes, in terms of its success in the marketplace, it's now in well over 100 different brands. It's more like 150 different brands. So that's another way of making sure things go into impact. That catalyst that I showed you that was able to split seawater and combine it with CO2, we were able to spin out a company called Catalytic Innovations. The technology that was further developed by us and Catalytic Innovations, that technology became the basis of a company operating in Brooklyn right now called the Air Company. The Air Company is using that technology to make all of those different CO2-based products. And while it starts off with various alcohols and other types of things, what it's pivoted to is how do you make sustainable aviation fuels and other types of fuels. The two biggest clients, of course, happen to be NASA and the United States Air Force. So this is how we take our biggest problem and turn it into our biggest opportunity. You won't be shocked that the large scale up being built now outside of Niagara is being built outside of Niagara Falls to take advantage of the hydropower. The one thing that I would want to mention is this study that was done, not by us, but I would have been biased, but by Columbia. And that showed that if you made the methanol, ethanol, and the sustainable aviation fuels, if everybody in the world made it by the Air Company technology, it would reduce carbon footprint by close to 11%. That's a big number. And yes, it's knock wood. still going strong. The last example that I'd like to mention is the African Power Initiative. The African Power Initiative, won't surprise you, is a double entendre for, yes, power in terms of energy, but power also in terms of empowerment. It started when I first arrived here at Yale many years ago, and it started with some of the unarable land that is located both in Uganda and Ethiopia, where nothing seemed to be able to grow. And we started saying, how do we start with plantings? How do we understand where to plant, what to plant, candle nuts, Simaruba, Jatropha, candle nut, and started those plantings over the years, starting in 2010 until now. What we're looking at is our hillsides. And you might say, well, that's a very nice little demonstration project. What I'm told is we're up to about land the size of half of the state of Connecticut, over 1 billion trees. And you say, well, that's a nice tree planting thing, a nice tree planting story. Turning the oil from the nuts. Do I have the nuts? I have the nuts. There you go. Who's good at catching? Let's see. Okay, there you go. Thank you. That is a candle nut. Would you like a candle nut? I'll hand you a candle nut. Why would it be called a candle nut? Because the oil inside, people use these as candles locally. So you take the oil. Oh, there you go. Nice catch. So you take the candle nuts and you get the oil out, and oh, isn't that great? You can make lots of biodiesel, and you, instead of importing lots of petroleum, you can do that. And awesome, right? Then you wind up with giant mountains of nuts. Giant mountains of nuts. Did you wonder why we took on splitting lignin into valuable chemicals? Those nuts are amazing sources of something called C lignin. And being able to break those down, all of a sudden, this idea of an integrated biorefinery being a very nice, cute little framework starts becoming real. So instead of just having piles of nuts, you now have, do you have fuel, energy, power? Do you have products that are sold on the world market at this point? And most importantly, do you build community? The answer is yes. So is this, that they have these trees, they're holding water, they're healing the soil. Yeah, they have their climate benefits. They produce energy. They generate local economies, jobs from harvesting, jobs from selling the products. And you're starting to get the feel of an ecosystem, of an innovation ecosystem, of an environmental and a sustainability ecosystem. Starting from those nuts, and we could go on and on. I'm going to finish by saying these few examples are telling you what we do in our labs, but more importantly, what we do around the world. The Global Green Chem Innovation and Network System that is we do in partnership with the United Nations, and more importantly, with partners around the world, is about saying, yes, we want to raise awareness. Yes, we want to build this network, but we also want to develop an accelerator ecosystem. So people are turning these discoveries into impact, turning these sustainable technologies into businesses that impact people's lives. And we're doing this with a focus starting with 6 countries, but a network that's touching 72 countries. Why do we do this? Because those of you who took high school chemistry heard the word valence. And valence, the first definition of valence is all about, yes, the outer shell electrons allowed to form bonds. But I'm not interested in that one right now. I'm interested in the third definition of valence. The capacity of one person or thing to react with or affect another in some special way, attraction or facilitation of a function or activity. That's the valency. That's the kind of bonds that we're talking about building, because it's the metaphorical molecules from our metaphorical periodic table that brings together, yes, the scientific and technological elements, but with those enabling elements, the investments, the economic models, the frameworks, the regulation, the communication, the education, those enabling frameworks are what allow us to turn theory into practice, to turn invention into positive impact. So what is it that we actually produce in our center? Well, we produce CEOs and founders of companies. We produce professors who are now all over the world. But most importantly, we produce brilliant inventors, scientists, and engineers who are writing policy, who are making investment decisions, who are communicating through the media, and are teaching the next generation. It is for this reason that I am so proud to be part of YSE, to be part of the Center for Green Chemistry and Green Engineering, because if any of you are interested in knowing what this global community looks like, what it's doing, and if you want to be a part of it, the QR code's there, sign up. There is no barrier to entry. This is an open party. And at the end of the day, what we want to do is design tomorrow so that it's better than today. Thanks so much. Hey, Dylan, am I supposed to answer questions?
Yeah, we have probably time for one or two questions. So,
Mm-hmm.
Hey, Paul, thanks for a great talk.
Thanks.
I want to ask you a little bit about some of your failures and the risks you're taking. And like, how do we do a better job? I feel like the environmental community is incredibly risk averse. And how do we get people to take on more risk and deal with failure more?
I'm not being glib when I say I struggle with the concept of failure because I just don't see it that way. And that's not a trivial response. It's a frame for how you move forward with innovation, from my perspective. So I agree with you that that there is a lot of risk aversity that exists, and quite frankly, I'm concerned with the institutions in society that we have, I'll say, trusted and relied upon to take risks, becoming the most risk adverse. When we look at our institutions, whether it's our capital investment institutions, whether it's our research funding institutions, and we are backing away from what brought us all this success of the future, that really is quite concerning. That's what brought us to the dance of innovation, and we're seeing that, as we all know, capital is flowing more toward apps than it is toward transformative pipe in the ground. So do I think that that's a large concern? Yes. Do I think that we spend a lot of time, I'll say, measuring, monitoring, reviewing, and assessing and characterizing the problem rather than focusing on the solution? I think that that's a big problem. Right now, we are swimming in a time when innovation is just staring us in the face. And so for the past, I'll say, 25 years, we have, as a science and technology community, have turned the impossible into the possible. When I talk about CO2 as one example, there are so many more examples of how what was viewed as impossible is now possible. We have an engineering community that's turned the possible into the practical, and we have a business community that is struggling because, I'm going to suggest, because of our economic models that we have almost a religious fervor for, of turning the practical into the profitable. If people are going to devote their lives to creating new financial models, then we no longer want to listen to, oh, this is a wonderful, sustainable technology. It's a shame that the economics don't work. What we want to hear is, this is a wonderful, sustainable technology. How do you make the economics work? I'll leave it at that. Happy to have a long conversation. Yeah.
we have to cut it off at 12:55 just because there's a class coming in after this. So just want to thank Paul for his time.
I
So
got, okay, thanks.